Let's move on with next presentation. We are a bit late. Professor Kapagheridis with the title Contact Profile Analysis of Resource Estimation Domain, a case study on a laterite nickel deposit.
Okay. I'll try to run this as quickly as possible because we're running 10 minutes late anyway. And you probably had enough of me anyway. This is my third presentation. Okay. I'm going to present a very simple but very useful technique for validating and generally analyzing the boundaries between different estimation domains. And, well, in resource estimation of mineral deposits, we normally construct three-dimensional models of geology, because the success of which depends normally on the quality of the database used. The geological model will control the quantities reported, so it's really important to get it right. And as it will define the volumes that are considered to potentially host ore, and thus get estimated using the whatever method we choose. In certain deposits now, ore can be distributed across multiple zones or domains of lithological or grade control character. And in some cases, just a minute, this screen just keeps turning on and off. I don't know what's happening. It's confusing. And in some cases, these domains can be in contact with each other and not separated by totally sterile material. Okay. Now, identifying estimation domains and modeling their boundaries can be a time-consuming process, and the estimation practitioner needs to be able to validate them before moving on to their estimation. The technique we present here, called contact profile analysis, is a useful tool to investigate the behavior of the transition from one unit to another, and can be used to improve the use of samples from neighboring units to estimate the grades of a given geological unit. Why would you do that? Because you want to have a smoother transition between two units, when that makes sense to do, of course, when you believe that there is a transition. And that can also improve your resource category around the edges, okay? Because when you cannot, let's say, steal samples from the other unit, you're forced to have very few samples, you know, towards the edge of the sampling area within a unit. So our case study, it's the Chuka deposit again. It gets really popular today. This is the second presentation about this deposit. As most people know, the nickeliferous mineralization in Greece is related to the geotectonic zones of Almopia, Pelagonian and Subpelagonian. The main metalliferous regions are situated in Lokris, Evia and Castoria. In the area of Agios Ioannis, which is in central Greece, there are large deposits developed and mined by Larco and belong to the Subpelagonian zone. The Chuka deposit is characterized by a saprolite zone, which is 1 meter thick, followed by a paletic-pisolitic horizon, 4 meters thick, the upper part of which is comprised of transported material. Lower Cretaceous limestone layers alternating with nickel laterite ore are conformably overlying the mineralized zone. This is just a bit of information about the geology. Mining of the Chuka deposit, as we said, has started in the 90s, or restarted in the 90s by Larco. There was some underground mining before, and the underground Rumen pillar voids are also modeled together with everything else. This is the location of the Chuka mine in central Greece. The modeling and estimation of the Chuka deposit was based on 218 drill holes, giving a large number of composite samples to use. All the samples have been assigned to different domains based on lithology, and the boundaries between domains have been modeled using a mostly stratigraphic approach, and have been used to flag blocks in the model before resource estimation. And in the image here, this is just a typical cross-section. You can see with different colors the different domains, different estimation domains, and the system that Larco is using to code these domains. They use a numerical system for some reason. And you can see what they are. Not everything is bearing ore, of course, and the most interesting domains are 20, 37, and 38. Both nickel and iron grade is contained in a database and is being used to do this contact profile analysis. You can also see the old underground workings, which are also found in some of the drill holes. So how does contact profile analysis work? As I said, it's a very simple tool to investigate the relationship between grades when moving from one unit to another or from one domain to another. And this can help validate the domains themselves and the modeling that is used to produce those domains, and also justify and control the use of samples from neighboring domains during estimation. Now, the way it works, we get samples from each domain paired with samples from the neighboring domain and at a specific separation distance. The pairs were constructed over an increasing separation distance. For each separation distance, we get an average grade of the first domain plotted against the average grade of the second domain. So average grades from the first domain are plotted on negative distances on the graph, and differences could be observed within the graph. Okay, if we talk about graphs, we should see them to understand what's going on. You can see on the graph here, the left side of its graph is the first domain. The right side is the second domain. The vertical line in the middle is, let's say, the boundary. And we can see what the grade is doing in moving windows from the boundary in either side of the boundary. Of course, this boundary is not actually a model. It's just moving away. We get samples from our database, which are coded to belong to domain A, and then samples which belong to domain B, and we check their average grade as we move away from each other. So, of course, we also need to pay attention to the scale, because that can be critical as to something looking like a big jump over the boundary when in fact it's not, or the other way around. Now, in any case, we identify what we call hard boundaries or soft boundaries, and we can then choose, if they are a soft boundary, to, let's say, borrow some samples from the other domain to do the estimation. How far into the other domain you would go in the case of a soft boundary depends on what kind of grade you had in the first domain in the first place, and you definitely don't want to change the statistical behavior of those samples as to that domain. So when we examine the results, I just give an example here. There's so many different boundaries here to talk about, and we don't have time, obviously, to do that. The contact profile between the overburden material, for example, and the conglomerate layer was constructed. The values near the surface between the interface between the two domains were considerably different, producing a sudden jump in nickel grade when moving from one to another, and a similar change in the iron grade in less than a meter of distance. That was considered to be a hard boundary, and no samples from 12 were used to estimate domain 18, which of course you would anyway, because 12 is just a different type of material anyway. The system also calculates some basic statistics either side to further justify calling the boundary soft or hard. And here you can see a number of different graphs from the different boundaries in this particular deposit. And it's quite interesting what happens, for example, between 20 and 37. We can see with the red lines the nickel grades, the average nickel grade as we move from one domain to another, and the iron grade as well with the dashed blue line. And we can see a kind of different behavior, obviously, for the iron and for the nickel in this case. Whereas in between 37 and 38, they both seem to behave in a similar manner across the boundary. There's a big drop when we go from 37 to 38 in both cases. So this is a very simple tool. There's not a lot of math behind it. It's very easy to do, even if you don't have specialized software to do it. to perform this. And we also get the basic nickel statistics between the different resource domains and what kind of boundary. We also get the correlation for the first interval, which can also help us make a decision as to the type of boundary. This is for nickel, and this is for iron. Sorry for running this too fast, but I think you'll all be happy with that at the end. So it's a very simple technique that can be used to investigate the relationship between grades, other side of the boundary, between neighboring domains. And the results of this technique can be used to increase confidence in the boundaries themselves and how efficiently they separate sample distributions and sample domains, and decide as to the type of the boundary, soft or hard, and in the case of soft boundaries, control the depth of sample exchange between domains. So thank you very much for your attention. This screen continues to do that.
Thank you, Professor Capagheri. There is one question.
Thank you very much, Professor, for your very interesting presentation. My first question is that did you use the blast holes at the end to validate your separation of the boundaries or not? And my second question is that for your separations of these boundaries, did you consider or did you add also the geological cross sections and the information, or you used only the grade data you had?
Can you repeat the second question? Because for some reason I started thinking about your first and I completely didn't listen to the second one. Can you please repeat the second question?
Yes. I just wonder if you, when you were doing your contact analysis, if you used or if you considered also the geological cross sections or like as indicators, or somehow did you consider your geological information while you were separating your contacts?
Okay.
Or not? Or you used only the grade data you had?
Okay. First of all, for the first question, in most cases of this type of mining, we don't have blast holes because there's little blasting, but the company does some grade control, so I think they are in a position to verify the grades. Now, for the second question, well, the domains were modeled in the first place using the geology and also the grade, okay? So we come after that step to do this contact profile analysis and see how well that model has worked for us, okay? So yes, they do use the geology, and I say they because it's LARCO and I'm just helping them out. And then we come and analyze whether this modeling, geological modeling actually worked for us for estimation. I hope I answered the question.
Any other question? No, so thank you, Professor.